Hi everybody and welcome. Today's focus is going to be looking at dependent probability. So your goal after watching today's video will be to understand when an event has a dependent probability and to be able to calculate the probability of a dependent event occurring. So a couple of things that we're going to take a look at to start here. First is different types of probability events that we're going to see. So our first definition is compound probability. And this definition is the chance that two or more events will occur together. So the idea here is that, let's say you're rolling two dice. Something that would be a compound probability would be like, what is the probability that both dice add up to 10 or more? The reason why this is a compound probability is because you need to roll two different die. If you don't have two die, then there's no way you can add up to 10, and it's also telling us we're doing two things. So a compound probability is specifically when we're taking a look at doing multiple things at the same time instead of just going through the one. So first, we must determine how many events are happening. Second, if we are solving for multiple events, so as in more than one thing happening, we have to determine if the first event changes the probability of the second event. In the case of our die, rolling one die and then rolling a second die, they're both totally independent of each other. There is no magnetic force that magically happens from rolling your first die that somehow changes what happens to the second one. So because of that, they don't change each other. They're just completely independently existing things. Third, the last thing, is we want to be sure we use the correct formula for independent and dependent events. So it's just a fancy way of saying if the first event changes what happens in the second event, we have to make sure that we are adjusting for that. If it doesn't change anything, then don't change anything for your second event. So the example of rolling two die is a great example of something that does not have any effect on the two. That would be an independent event because, like I said, they're not going to affect each other. Another great example of this is if you have two spinners. Spinning one spinner and then spinning a second spinner, they don't change anything about each other. The spinner is exactly the same before and after it's spun. So because of that, they're not being changed by the other one being spun. So if we take a look here using two spinners, we're finding the compound probability because we are trying to do two things at a time. So for our first one here, let's actually take a look at this one right here, number 6, the probability that you get an A and the probability that you get a 2. So an A out of 4 outcomes, it's one of the 4. So we'll say that that probability is 1 out of 4. And the probability of a 2, it actually looks like there are 2 2s. So that would be 2 out of the 6. And specifically for a compound probability, what we're going to do is we're just going to take the two independent probabilities and multiply them. So when we do that here, what we're going to see we end up with is top times top. So straight across here, 1 times 2, get 2. And then on the bottom, bottom times bottom again, so 4 times 6, and that'll get us 24. You're welcome to simplify that to 1 over 12, but we're also just as happy with 2 over 24. So now I'm going to ask you to jump into the second one here, the probability of getting a D and the probability of getting a 1. I'm going to ask you to solve this one in Canvas now. So taking a look at this, start off with the probability of getting a D. So 1 out of 4 outcomes gives us a D. And then we multiply that by the probability of getting a 1. So we see 1 comes up 1, 2, 3 times actually out of the 6 total sides of the spinner. So on top, again, multiply straight across on the bottom as well. You get 3 out of 24. Again, you are more than welcome to simplify that to 1 over 6, but we are perfectly happy with 3 out of 24. So these are all independent events because the probability of D and probability of 1 don't change. They'll always be 3 out of 6. They'll always be 1 out of 4. And that's an example of our first side. So the second side of what we're taking a look at today is what happens when the first event does have an impact on the second event. So we call this dependent events. So when we have dependent events, this is just saying that the outcome of the first event changes the outcome of the second. I like to think of a bag of Skittles. So if we have some Skittles, and let's say we have a few, so we have like yellow ones, gross. Red ones, much nicer, much better tasting. And then, honestly, my personal favorite, if I can find it here, I'm very bad with colors, is purple. I think those are like by far the best. So in this bag of Skittles, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Hopefully I counted that correctly. So we have 9 total Skittles. And let's say I'm looking for the probability that I get a yellow and a yellow. So probabilities of these are out of 9. But what happens is when we take a Skittle, when we go to get our second Skittle, we've already taken one out and we've eaten it. So our second event actually decreases. We go down to having 8 in our whole. So we're trying to get a probability of a yellow and then probability of another yellow. Well, let's say we take that first yellow out. There's 3 out of 9. And then all of a sudden, this yellow is gone because we ate it. Well, now there's only 2 left out of 8 total Skittles in the bag. So we've already eaten one of our yellow Skittles, so it goes down to just 2 from 3. And we've eaten one of the Skittles in the bag, so it goes down from 9 to 8. So because this second event is changed by eating the first Skittle, that's how we know that it's a dependent event. So our probability of 2 yellows in this case would be 6 out of 72. Or 1 out of 12. Again, totally fine if you want to simplify or not. It does not matter to me. But the big idea here is that when we're going through and calculating these, we have to be sure, is that second event, is it changed by eating that first Skittle, by having that first event? So first, we need to calculate the probability of that first event. And then second, we have to determine how the outcome of the first event changes the probability of the second event. And then lastly, we have to adjust the probability of the second event, then multiply the 2 probabilities. Basically what this is telling us is that we just have to calculate the probabilities and make sure that we're accounting for eating the Skittle, or when the whole changes. As long as we do that, we're in good shape. So very similar to our Skittles bag, we're going to be taking a look at some tiles. So we're drawing 2 tiles from the collection on the right, and we're trying to find the compound probabilities. When we draw the first tile, we are using it. So because it's being used, it's in our shopping cart, it's no longer in our sample anymore. So if we're looking at the probability of an A and an A, I'm actually going to ask you to solve this one first. See what you think. All right, so taking a look here, we first have to determine how many tiles do we have total. So we have 15 if we count them. So counting our 15 tiles, and we look at A's, we have 2. So let's say that we do, in fact, draw that A first. Well, that would leave us a second probability with only 14 tiles left, and specifically only 1 of the A's are left. So on top, 2 times 1 is 2, and on the bottom, 15 times 14 gets us 210. Again, able to be simplified, but we're happy with it like that. Totally up to you. The second one, I'm going to ask you to solve this one as well, because there's another small feature here that we need to take a look at. So let's solve number 16 now. And same thing, so probability of R. So we have 15 tiles total. Of those tiles, we have 1, 2, 3, 4, 5, 6 R's. We use one of the R's, so we're down to 14 tiles total. And now we're looking for a C. So because our first pick was an R, we still have all of our C's left. We still have 3 of those C's left. So here we're happy. 18 on top, 6 times 3. 15 times 14, or 210 on the bottom for that answer. Okay. So that's the idea for today. The big thing is taking a look at, after we draw that first one, specifically, what did we draw? So if we drew an A, that means that one of the A's is gone now. If we drew an R, one of the R's is gone now. Secondly, taking a look at our decrease to our hole. So we've taken one of the holes away, so that makes our bottom go down. We have to be careful on the top, though. The only way that our top goes down is if we've already drawn the thing that we're looking for. So in example 15, we already drew an A, and we were looking for another A. That's why the top changed. But in example 16, we didn't take away any C's. All 3 C's were left, so the top didn't change for number 16. So be really careful with that, because almost always for a dependent event, your bottom's going to change, but sometimes your top does, and sometimes it doesn't. And that's normally the place where we get tripped up. So hopefully this video helps with some of those basics. You're ready to jump into the practice questions now. As always, let me know if you have any questions.